Suppose there was a farmer named Bill, and Bill had two children. Bill, well, he owns a triangular pasture with a well situated somewhere within this pasture. He wishes to split his pasture into two smaller pastures, equal in area for his children. But since he wants it to be completely fair for the two, he also wishes that both pastures have access to the well, because there is one and only one well within this large pasture. It would not be very cool for the other if only one of the two children gets to keep the well entirely. He wishes you'd help him run the fences from the well to form his children's two pastures. The problem is, Bill doesn't really know what the area of his land is, and neither you nor anyone Bill knows can find out. He really wants you to help him, though. He's working on an accurate map of the pasture. He wishes that as soon as he writes up the map, you immediately start constructing, with a pencil, where the fences should run. You think about it and you think about it more until you realize that this is just a geometry problem you probably have done in high school. Quite literally, this problem is straight out of my homework from high school. This problem, in geometric terms, can be translated as given a triangle, meaning it could be whatever. Since we don't know the measurements of our pasture, it could be a right triangle or obtuse triangle, and it could be any size, big or small. And given an arbitrarily positioned point within this triangle, how can one completely divide this triangle by construction two shapes equal in area such that the two shapes share the given point and don't overlap? By the way, since we are talking about the general case, we need to formulate a strategy that applies to any scenario. If we can find a solution for a generalized problem, then we don't need to know what the area of Bill's pasture is or where the heck this well is situated. But how do we even begin to solve a problem like that? You should realize by now that this is a construction problem, so it's probably good to review what geometric construction even is. The first prominent place geometric construction was held is in Euclid's Elements. That's why they're often called Euclidean construction. Anyways, since this is his thing, we should probably follow his rules. Euclid only had 2 rules. Well, actually he has 5. We call them postulates, but that's not what I'm talking about. His 2 rules in construction are that we are only permitted to use a straight edge and the compass, except for the pencil or whatever you're using to write pen, of course. We use the straight edge to make straight lines and the compass for not so straight lines. I know I'm working with a ruler here which has measurements, but we are not actually allowed to use this to measure. Especially since we want to find a generalized answer, we must work with arbitrarily measured lengths. With only these 2 tools, and a pencil of course, there are a plethora of things we can construct. It's kind of crazy if you think about it. Okay, but what really is Euclidean construction? What's the point? Why are we doing this? I like to think about it this way. We obviously all know what algebra is. We usually define algebra as the mathematics of unknowns. We work with variables that we don't know the value of. The purpose of algebra is to enable us to perform mathematical operations despite not really knowing what the values of x or y are equal to. In the same way, I like to think of Euclidean construction as a form of algebra that works with shapes and lengths that we can't really measure. We can add, subtract, multiply, divide, square, and even take the square root of an unknown length. I believe it's an important skill to learn, and it's pretty cool, so yeah. It's the algebra of shapes. How cool. Going back, the problem requires us to form 2 shapes of equal area. But how do we even calculate the area of a shape with lengths we don't have a value for? How can we compare the areas of 2 different polygons if we don't know what their area is? Hello everyone, before we continue, I really wanted to do this small activity just so that you can, what was I gonna say? Just so that you really understand what I was talking about in that question. Alright, so we got here a pencil, and in a short while I'm gonna be putting a piece of paper here, and what's gonna be on that paper is there's gonna be 2 shapes. Right, so there's gonna be one shape here and another shape here. And the activity is you guys have to tell me which one of those two shapes is larger? Okay, that seems easy enough. The catch is you don't know what their measurements are. I mean, you can clearly see them and we can sort of measure them, but we will never know what their exact measurements are. So it's kind of like unknown, right? Here we actually have a ruler, so we could check real quick how large they are. But for the purpose of the activity, let's just pretend we don't have this, okay? So we don't have it, and we're not allowed to use it. Okay, so let's just bring in our first example. So you guys have to tell me which one of these two shapes is larger. So this shouldn't be too hard. Now I want you guys to tell me which one of the two shapes is larger. And when I say larger, I mean by area. Obviously, this is larger than this, but it's very important to really rigorously give a reason why that is. How do we prove that this is larger than this? I mean, it obviously is, but how do you, what's the reason behind it? So again, when we're talking about, like, when I say larger, I mean area. And when we're talking about area, it's probably good to mention that the area of a triangle is equals to 1/2 base times height. I'm just gonna name some stuff here. So I named this one B for base, and then I'm just gonna quickly draw a line. This is gonna be height. Okay, and we're just gonna do the same thing here, but this is base prime, height prime. So what we want to prove is that this triangle is larger than this triangle. Okay, so one very good thing to practice is just put it on top, what you want to say. So at the end, we want to be able to say that 1/2 base times height is larger than 1/2 base prime and height prime. Okay, so how do we do this? Well, the base here clearly is bigger than the base here. And we're just gonna assume everything is drawn like perfectly to scale. So we should be able to say that, okay? Because usually you're not allowed to say that. I mean, it looks bigger, but that's not a reason why it's bigger. But let's just say here, you know, it obviously is. We could check with like a compass. You know, we don't have to check, you know, but just look at it. We're doing this, you know, just casually look at it. Base, this base is bigger than base prime. So let's just say it here, right? I'm just gonna make like a divider. So we can say base is bigger than base prime, right? Obviously. What else can we see? Well, we can see like very clearly that height is also bigger than this height here. So let's just say height is bigger than height prime. And just from those two information, we can actually just prove this statement right over here that I just wrote down for you guys. Because this is bigger than this, and this is bigger than this, therefore their products, right, the products of base and height should be bigger than the product of base prime and height prime. So we should be able to say base and height, so multiply. So if you multiply that, that should be bigger than base prime and height prime. That's just a basic inequality. You know, since both of these two are bigger than both of these two, if you multiply them, I mean, it should be bigger. Clearly, it is bigger, right? But it's very important that we're just writing this down. And now for the final step, all we can do is, well, we can just multiply 1/2 to both sides. And now we get what we wanted to state at the beginning, right? We can multiply 1/2 into both sides because that's just an axiom, right? Equals multiplied to equal, or not equals. Inequalities, if you multiply equals, right, it's the relationship will stay the same. Okay, now let's look at a different example, and this one's gonna be not so easy. Let me just show you this one. So now we have two triangles, and it's right away, just by looking at it, you're not gonna be able to see, well, I mean, now that I'm looking at it, one of them does look larger than the other. But it's not very good to just rush into conclusions. We must do this still with a bit of rigor. So what we can do the same thing. So let's just name stuff again. All right. So let's see, what do we have here? All right. So if we do the same thing we did earlier, we're gonna be running into some problems. Okay. So the base here. Let's compare it with the base here, right? What we just did earlier. Now, if you look at it, this is clearly smaller than that. So we should write base less than base prime. This is clearly smaller than this one. So height this time is actually greater than height prime. Now we've run into a problem because look at this. You know, we're not going to be able to deduce anything from this. Unlike earlier, it was very obvious. Since both of these were larger than both of this, that means their products must be larger. But this is mixed. So it's not going to be so easy to deduce. I mean, for all we know, it could be equal. I'm thinking of like an example right now. So let's just focus our attention here. Let's just say 4 and then 4, and then we get 8 and 2. You can see 8 is clearly bigger than 4, and 4 is clearly bigger than 2. But if you multiply them, we'll be left with 16 and then 16. 8 times 2 is 16. Yeah, but they're actually equal. So they could even be equal, but I doubt they're equal. But they could be. This is a problem. How are we gonna do this? One thing we can do is use a different method. So instead of just base to base and height to height, we can compare whichever is bigger. So the bigger one versus the bigger one versus the smaller one and the smaller. What do I mean by that? So let's just say here, which one's the bigger one? This one's the bigger one. This one's the smaller one. And this one, it's not so obvious which one. Let's check with the compass. It's really big. Okay, so that's pretty much the same. Okay, so this one, the base is small. The base is bigger, sorry. So it's gonna be height versus base, and then base versus height. And in that way, we can sort of systematically compare them again. So height versus this, what do we get? Well, actually, this height is a little bit bigger than base prime. So actually, height is bigger than base prime. Yeah, but the problem is if you go here, the base is actually smaller than height prime. So base is less than height prime. So again, we run into that thing. We run into that thing where it's like, oh, it's kind of mixed up. So what's up? You know, this is bigger than this, but this is bigger than this. So it's not so obvious how we go on about this. What you can do, if you're a madman, is just keep doing this, but with different bases and with different height. So this doesn't have to be the base. You can sort of flip the picture and instead use this as the base. So you can kind of erase this and you can kind of erase that and then use this guy. That was not correctly drawn, but you get the point. This is gonna be the new height. So this is the height and this is the base. And then you can, you know, now you can try that. And then maybe you'll get something, and then if that doesn't work, you can try this other one, and then, you know, whatever. But that's not very easy to do. That's gonna take a lot of work. We want a way to be able to compare two shapes and their area in an easy way, in an easy fashion. We want to be able to do it in just one strategy. What's worse is these are just triangles. What about like 4-sided polygons or 5-sided polygons and more? How do we tell the relationship between two shapes generally, like in a general case? So we need a strategy that applies to whatever shape. How do we do that? Well, just keep watching. Let's go back to my description of Euclidean construction, which is that it is simply the algebra of lengths and shapes. Let's ask yourselves first, how do we even compare the area of two shapes algebraically? Well, we multiply the lengths and express them in square units, right? It could be inches, it could be feet, whatever. Square units. And then we compare the coefficients to see which of these two shapes is larger. Did you catch that though? I said square units. By definition, we express the area of any 2D shape with squares. We can actually translate this into pencil and paper we can transform two given polygons into squares and then check with a compass which square is larger by comparing side lengths. Hello everyone, this is Behind the Scenes Terrence, and what was I gonna say? Oh, so I made these two triangles, right? So what I did is I just plotted 3 random points on the paper and just made a triangle with them, and I wanted to use the method that I proposed in the video to know which of them have better area, which is that we first transform them into a square equal to that thing, right? And then compare the squares and then check which one of the squares is larger, right? So let's just say if this square was larger than this square, then that logically means that this square is bigger than this square. But what's crazy is that when I check it with the compass, you see, you measure it like this, you see that's equal, and then you go right down here and you measure it like that, they're literally the same square. And that's crazy because these are just 3 randomly plotted points, and I somehow got 2 triangles which are equal in area. I mean, there could have been some error, but for the most part they are really close, very close in area. So I don't really know what to do with this, you know. I can't really use this as an example because they're not really equal, they're just very close. And yeah. It's just a funny coincidence. Okay, so now we know what to do. Just transform the polygon into a square. That is definitely trivial. How do we even do that? Again, let's look back to how we do it algebraically. Let's start with the simplest polygon, the triangle. How can we construct a square equal to a given triangle? When we're talking about equality of shapes, we are referring to the equality of their areas. Well, the area of a triangle can be expressed as 1/2 base times height. Don't forget about Heron's formula though. But let's just stick to what we're more used to, 1/2 base times height. The area of a square is just side squared. If you want to construct our square, it's probably good to know what the side length is. So that's probably what we're looking for, right? We're gonna be looking for this side. So let's solve for s. The square root of 1/2 base times height is equal to the square side length. Wow, that was super useful. Okay, but it's still not obvious enough for us to just start constructing. It's really not obvious. How do we do this? Okay, so let's look back at our problem in a different way. Going back to the original equation, we can rewrite s squared into s times s. That's by definition what squared is. What can we notice here? Well, our equation is composed of equals which are products of 2 numbers. Does that ring any bells? This is one very important trick to know when working with products in geometry. The fact that this is true allows us to make many constructions that would otherwise be impossible. Okay, so what do we have here? Our equation is composed of equals which are products of 2 numbers. What do we do with this information? We can make a proportion. Do you remember the saying, product of the means equals product of the extremes? Both s's can be the means, and 1/2 base and height can be extremes. We can rewrite our equation to a proportion, and now we can finally construct this. How, you might ask? Well, everyone should know this. In geometry, when we're talking about whatever ratios, proportions, fractions, the best way to construct this is through similar polygons. We just need 2 similar triangles that have sides 1/2 base and height respectively, and that share a given side. That given side will be our square side length. Hello everyone, this is actually my second take. My first take took like 30 minutes long because I got too carried away of talking, and I kind of don't want it to last that long. I don't want to edit that. So yeah, we're doing this again. In the video, I believe we were discussing about transforming a triangle into a square. Then we wanted their areas to be equal, obviously, to transform it. So what we had was Let me just see, because I keep writing stuff and it doesn't end up being in the frame. So 1/2 base times height equals to side squared. And since we wanted to construct the square, we decided to solve for s for side. If you're just looking at this for the first time, that you know, it's not obvious. How do you do that? How do you just construct this? Well, lucky for us, people from the past have also wondered how to do this. They left us with a pretty nice solution to constructing lengths like this. So how do we do it? Before we actually do it, I want to tell you a key concept that make this possible. And this thing is what we call the mean proportion. So you probably already know this, but just to review, the mean proportion, well, as the name suggests, it's a proportion. It's a proportion, right? So what is a proportion? Well, it's just common fractions or common ratios. So it could look something like this, right? Or if you want fractions, you know, I just like them like that, ratios. But you can also do fractions like this. Yeah, like that. So a mean proportion is when the means, just to review by the way, these are the means, and then these guys here are the extremes. So it's when the means, or it could even be the extremes, but either one, if both of the means here are equal. So a mean proportion would look like A is to B as B is to C. So you can see here is the same thing. I did not write that correctly. There we go. Now the fraction would look like A B equals B C. And if you guys remember, the product of the means equals the product of the extremes. You just multiply B and B, and you just multiply A and C, and it should be equal. If you remember elementary school, they actually teach us cross multiplication, and this is literally it. Cross multiplication. You just go like this, and then you just go like this, and then you multiply. So this is gonna be AC equals B times B, which is B squared. But we want to know what B is, so let's just solve for B, and we're going to be left with something similar to what we have here actually. The square root of AC equals B. And that's awfully similar. Look at that. They're actually just the same thing. So we want to be able to make this happen with our lengths here. And how do we do that? Well, as I mentioned in the video, the way we do that is through similar polygons. What we're going to be using is what we call the ratio of similitude. That's supposed to be a U. So what is this? It's basically just the ratio of the corresponding sides of similar polygons. So let me just draw some triangles, and then let me just draw the same triangle but bigger. And I'm just gonna say these are similar. What that basically means is all their angles are equal. So the angles are equal, and the sides are proportional. The ratio of similitude is the proportion of those sides. So let's just say here we have a 3, 4, 5 triangle. Here we're gonna have a 6, 8, 10. The ratio of similitude would be the ratio of each corresponding side. So here it's 3, 6. Like that. And that's actually all you need, and that's actually the ratio of similitude. 3, 6 is also 1/2. So 1/2 is the ratio of similitude, because if you notice, if you do it for any other side, 4 8ths, that's just the same thing. That's really 1/2. Also 5/10. Actually, similar polygons have 2 ratio of similitudes. It's the first one you get, and then it's what is it called? Reciprocal. Because you can do like the opposite. Instead of 3 6, you can do 6 3, right? Or like 8 4, or like 10 fifths, right? And that would be 2 to 1, which is just 2. So yeah. So what we want to do is we want to find a way where you see this 3, 6, 4, 8. We want to find a way to get the 6 and the 4 to be equal, right? Because we want to have this same construction here. This one. Lucky for us, there's actually a theorem that makes finding these polygons very easy. The same theorem is actually used to prove the Pythagorean theorem. I'm just gonna grab for us a brand new paper. This theorem states that if you have a triangle, but not just any triangle, if you have a right triangle, sorry if this is small, and you draw the altitude onto the hypotenuse, you will be left with 3 similar triangles, namely these triangles. So just to think about it, you see this CPB, that's similar to the entire triangle ABC, which is also similar to this triangle here. Now the reason why my first try recording this was so long is because we actually did the proof live here. I'm not gonna do that, although I'd love to. We don't have time. That's just gonna take too long. So we know that these triangles are in fact similar. I'm just gonna name more stuff, so I'm gonna name this A because these are the sides that we're interested in. Oops, the recording actually got stopped, and we got spoiled to the the important part. So just just pretend this is not here. So I'm just gonna scribble that out. But now you know where we're going, right? So the reason why I named these is these are the important sides, and what we want to find from them is their ratio of similitude. Now let's think about how we got the ratio of similitude earlier. We got corresponding sides and we just simply put them in proportions, right? So you see we got this side, we found which side corresponded to it, and then we put 3, 6. And we want to do the same here. We got here A, right? Now we want to find which side corresponds with A. Now we're going to be looking at the smaller triangle, so we're just going to disregard ABC here. So we're only looking at these 2 triangles. Now which side corresponds with A? Now it's not obvious here because there's a lot of drawings. Not so obvious which one corresponds to which, but the way to do it is you look at the letters and you see which one correspond to them. So here you see A here is actually AP, and you look at which letters correspond with A and P. Here it's actually C and P. So this is AP, so A corresponds to C and P, which is B here. That's why I wrote this. So that's why we write this A is to B, and then equals, and then you know where this goes, but let's just do it anyway. CP, which corresponds with CP, it's BP, which is also C. That's why we have B is to C, and this is what we're looking for. This is the second try, so it's kind of funny seeing this. But yeah, this is what we were looking for, and we do product of the means equals product of the extremes. We are going to be left with AC equals B squared. Now you take the square root AC equals B. Okay, now we take this same thing, right? And I'm gonna draw another right triangle right over here. But instead of having A, B, and C, we want one side, so let's just have this, I'm gonna name this B. We want one side to be 1/2 base, and then the other side to be height. And then this, whatever this will be, that will actually be the side length. Because let's put it in the thing again. A is to B as B is to C. 1/2 is to S as S is to H. Now we can do product of the means equals product of the extremes. So it's going to be S squared equals to 1/2 base times height. Now we just take the square root. Square root 1/2 base times height equals S. That's how we find S. You see, that's what we wanted here earlier. Square root of 1/2 base times height. Now we're gonna go backwards, make a proportion, and then construct it like this. And that's how we do it. How do we do it? Again, we're gonna be using a very neat, I'm just gonna get another paper, neat theorem, which is that when you get a circle, actually this time I'm gonna be constructing it seriously. So I'm just gonna name this point O. So we have point O here. And then we have our compass. Here, I'm just gonna make a big circle. Hope you guys can see it on screen. It's not centered. There we go. Now if we have a circle like this, and then we construct the diameter is a chord that passes through the center. So diameter. There we go. And then we're gonna name it A, B. And now we pick any point within arc AB. Actually, any point on the circle except for A and B. So we just pick a random point. Let's just say here. I'm just gonna like do this. Let's call it P. If you connect A and P and B and P, wherever P is, this will always be a right triangle. And it's just a cool little fact. And actually, if you're watching this from 3 blue 1 brown, or 3 brown 1, no, it's 3 blue 1 brown, this is actually the logo, right? This is what the logo is, this theorem. So we can use this to construct our thing. Now we can do like I'm gonna construct this properly. Okay, so now I'm gonna make the altitude. So the altitude goes about here. Now that we have the altitude, we have now similar triangles. So this triangle here, I'm just gonna shade it. This is similar to this triangle. That's how we're gonna get our square side length. Instead of having this circle and then making the triangle from there, what we actually need to do is we need to make the hypotenuse first. We need to first make this. So we get our compass, and we sort of set it here to whatever the 1/2 base is. And then we do again for whatever the height is. And then we do this backwards. Okay, so I don't want to waste too much paper, so I just flipped it around. I'm gonna make a triangle like this. Very simple triangle. So we already got the base, so this is gonna be our base. So base, now we need the height. Okay, so we got our height going for us. Now we wanna make the diameter thing, right? We wanna make this AB. So I'm just gonna make a long line right over here, and then we're just gonna measure the lengths onto it. So I'm just gonna get height first. So this is how you measure stuff. You just get the compass and you notice that they're equal, and then you just put them here, and now you've successfully placed this height over here. Make sense? Now we're gonna put the base as well. Now remember, this is the base, but the formula states 1/2 times base times height. So we can half either. I'm gonna be halving the base because 1/2 base is just, I don't know, preference. So I'm gonna half the base real quick. Now that the base is halved, we can sort of do the triangle thing backwards. Okay, so what do we need to go here? So we already got the diameter, so we probably need to find the center to make our circle thingy. So we don't have to draw the entire circle, we can draw like a semicircle. And then realize from the point at which they sort of meet, this part here and then this part here, there's a perpendicular going upward. So we're gonna make this first. So this is where they meet. We're gonna make the perpendicular there. Doesn't matter where we go. I'm just gonna go really high up. So this is our diameter. And now we got the altitude. And now we just need to find this thing's center and draw the semicircle, and we should be able to get it. So the center is right about here. Oops. Right about here. Let's check. Yo, that's actually like close to perfect. Okay, so we got the center, and now all you have to do is make the circle, and we got it. This is the point that we needed. We don't have to do this part, but it's cool to just make the triangle. Okay, so we made the triangle so that you guys can really see. So this is A, this is B, and this is C. A is to B as B is to C. And remember, this A here, this is actually the height. And this C here, this is actually 1/2 base. Therefore, this B here is actually our square side length. Now you can take the base and then make like your own line somewhere else and then make a square, but I'm too lazy to do that, so I'm just gonna do it here. You get B, right? So you measure, or not B, the square side length. So you measure S and you just drop down like this. Boop. And then you get that same thing and you make arcs. And ta-da! Square! Look at that! Right, so this triangle here, the area, so I'm just gonna write T for triangle. Area. I'm just gonna write it like that. And then the square, I'm just gonna write S, sub area, is equal. So they're actually equal. That's because we constructed them that way. This square has to be equal to this triangle. And it's because of all the, the math things we did. Isn't that so cool? I don't know. I think it's cool. Let's just remember why we're even doing this. It's because we want to take two different shapes and we want to compare their areas, right? So we have this triangle, and let's just say we have another triangle. Let's just say we have this monster triangle here. So we got this triangle. Now we don't know which one's larger. Maybe this is larger, maybe this is larger. Now what you can do is you can make a square equal to this triangle. And now you got two squares which are equal, and it should be very obvious which of those two squares should be larger. You just measure the thing and then you see which one's larger, and you got it. You're done. So now we know how to transform a given triangle into a square. But how do we do it for any polygon? Before we tackle that, let's talk about an important property of a triangle. We have already mentioned that the area of a triangle is 1/2 base times height. What that literally means is that we can take 1/2 of either the base of the height, it doesn't matter which one, so let's just stick with the base. We take 1/2 of the base, and then we take the height, we multiply them, and that's the area of the triangle. What's really neat about this is that as long as the base and the height remain the same, we can transform this triangle however we want to and still have the same area. The line through the vertex that is parallel to the base is the locus of points that preserve the triangle's original area. We can take the height and construct another line parallel to the base that distance away below. That is also part of the locus of points that preserve a triangle's original area. What that basically means is that we can place the vertex of our triangle anywhere on these lines, anywhere on these parallel lines, and the triangle's area will remain constant. It doesn't matter where we put it. We can place this vertex infinitely away from the base, giving us an infinitely sized perimeter, but still preserve the triangle's area, which means despite having a perimeter of infinity, we remain with a finite area. Is that not crazy? Another important fact that you must know is that any polygon can be triangulated. In other words, any polygon can be decomposed into a number of triangles. Now, we're not going to be proving this, in this video, but do trust me on that. You can search up on Google or somewhere, triangulating polygons, proof for that. We're not going to be doing that here. We don't have enough time for that. To be exact, a polygon with n sides can be triangulated into n minus 2 number of triangles. So for example, we have a pentagon, right? If we triangulate this, we will be left with 3 triangles. These two known facts allow the transformation of any polygon into a square. By triangulating a polygon, we are allowing ourselves to be able to freely transform and change the way the polygon is shaped without changing its area. Hello everyone, this is Terrence here, and we're gonna be voice-overing this dude doing this construction, in our case, transforming a given quadrilateral into a triangle. So here we're going to be extending the base. You're going to see in a second why we did that, but the important part here that I want you to focus right now is me joining A and C. And that's important because that forms the triangle ACD. So you can see that triangle over there. And what we're going to do in a sec, what I'm doing right now is I'm making the parallel line on point D. So parallel to AC. And what we're going to do is we're going to take the vertex, and remember, as long as it's parallel to the base, we can move around the vertex. So we're going to move the vertex D onto the extended base. You see the A, we extended the base there. We're going to move D down there. And what that does is we're going to make D basically collinear with A and B. And once it's collinear with A and B, you see the A there, bottom left, that's no longer going to be a vertex, because remember, a vertex is like the corner, is where the edges meet. It can't be on the edge itself. Now that it's on the edge itself, it is no longer a vertex. So from 4 vertices, we're going to minus 1. So now we only have 3 vertices, and 3 vertices, that determines a triangle. So now you can see A prime, B, and C, that's a whole new triangle, only because A is no longer a vertex. Make sense? So, and since A prime and D, A prime and D is parallel to the A and C, this whole thing is still constant. The area has not changed. That's why I'm writing here, the area of A prime, B, and C is equal to the area of A, B, C, D. So you see A, B, C, D. I actually did it in different colored pens so that you can sort of see it, although as I'm voice overing this, I can't really see much of the difference. Well, maybe because my hair is on the way. But yeah. Now I believe we are sufficiently ready to tackle the problem I first stated at the start of the video. All of that was just preparation to fully understand what the solution is, so that it's not really fuzzy when I show you the solution. Given a triangle with an arbitrarily positioned point within the triangle, how can one divide this triangle about the point into 2 shapes equal in area? A good practice when solving math problems is to start off by answering similar but simpler questions. How can one divide a given triangle into 2 smaller shapes of equal area? We just have to divide it in half. This one should be pretty easy for everyone by now, considering this is all what we've been talking about. For the people who don't know yet, challenge yourself to figure out how before I reveal the answer. Okay, so we talked about earlier how we can place the vertex of a triangle anywhere on the line, a distance away, parallel to the base, and the triangle's area will remain constant. If you think about it, we can do the opposite too. We can fix the vertex at a point, then we can extend the base, since in Euclidean geometry, that's very legal. Just extend the line, and anywhere on that line, we can move the base around, and we'll be left with a constant area. Consider the equation, 1/2 times 1/2 base times height equals 1/2 times base prime and height prime. So to just explain what this equation really means, we're looking for a triangle that is 1/2 the area of the original triangle. That's why we have the extra 1/2 of the left. So let's just do this algebraically. Multiply 2 on both sides to cancel out the 1/2s and be left with the equation 1/2 base times height equals base prime and height prime. I'm sure there is an infinite number of solutions for this, but the simplest probably is to just have base prime equal to 1/2 base and h prime equal to the given triangle's height, which means all we have to do is divide the base's length in half and connect the base's midpoint to the vertex, and we're done. Two triangles equal in area. So how do we do it about an arbitrarily positioned point within the triangle? It only took us 40 minutes of rambling, and now we can finally try to solve the problem head to head. So as I'm drawing this problem, let's even try to remember what the problem is all about. Bill here is drawing for us his triangular pasture in this triangle ABC. He wants us to specially take note of point P, which will be within ABC, and it could be anywhere, so we don't know. So I'm just gonna randomly put point P maybe right over here. Now we want to generalize this problem, so your triangle might look something else. You know, Bill might draw a different looking triangle. Maybe it's smaller, maybe it's bigger. Also the point, it could be here, it could be way over here, it could be way over there. It doesn't really matter. The point is we don't know where exactly point P is or what exactly the measurements are. To prove that no matter where P is or no matter what the lengths are, our construction will hold. So the problem was, from point P, he wants us to make two shapes which are equal in area. So how do we even go on about solving this? One very good practice to do when you're solving these math problems is to look at the question in a different way. Maybe reframe it, think about it in a different way, try to solve it in a different manner. We might be too focused trying to construct from point P new shapes that are equal area when we could be doing something else. Remember, all we need are two shapes which is equal to 1/2 of ABC, because that's basically what we're trying to do. We're trying to divide this triangle here. So as long as both shapes are equal to 1/2 ABC and they're within the triangle, then we should be good to go. Also, don't forget they have to share point P. So how do we get two shapes which is both equal to 1/2 of ABC? Well, we've already done this earlier. Just draw the median. So here we're going to draw the perpendicular bisector, and from the midpoint we are going to join it with point C. We're going to call the midpoint D. And now let's look at the problem like this. So instead of a triangle and then the point P, think of the triangle with the median and then you put point P in it. What if P happened to be on CD? Then we would be done. We would be finished. If P was here, well then we'll have satisfied what Bill wanted. You see, both shapes will share P and both shapes are equal area because this is the median, remember? But unfortunately, our P here is actually outside of this line. So we're going to have to do a bit more work. So what can we do? Well, realize that these already represent 1/2 base, or not 1/2. These already represent 1/2 ABC. So I want you to think about it this way. Instead of having to construct new shapes, we can make use of the fact that these are equal to 1/2 the triangle. Instead of constructing, we can transform one of them so that it includes P. So I'm going to be doing something. I'm going to be connecting P to D. So from P, I'm going to draw a line through D, ending at P prime. I don't know if you could see it. P prime is right over here. P prime could be anywhere. I just wanted to extend it. We're then going to connect C and P. And here is where the magic starts. So we're going to get this angle here. We're going to copy it and put it here. And what that will do is we're going to have parallel lines. Okay, so now from point D, I will construct a line parallel to PC. So I'm just going to go like this. Boom. And we're going to call this new point over here point E. Now I want you to notice this part here. You see CDB. Look what DE did to that triangle. So DE actually split CDB into two triangles. So we have here CDE and BDE. So we've decomposed this one big triangle into two smaller triangles. So I'm just gonna write that here. Triangle BDC, I forgot the little triangle thing, equals triangle CDE plus BDE. Now, what we want is this shape to include P. So what we can do, since, look, notice, these are both parallel. This line is parallel to this line. So what we can do is we can get C and we can push it all the way to P. We're going to connect P and E, and that should give us a triangle that's equal to CDE. These lines are parallel, so pushing this down is very legal, PDE. So let's write that down here. Triangle PDE is equal to triangle CDE. Now I want you guys to take a look here at this quadrilateral PDBE, or I guess BDPE. Notice that BDPE is actually just this triangle, triangle PDE and BDE combined. So this quadrilateral is just this triangle plus this triangle. And look here over the top, we can actually see that PDE is already equal to CDE. So we can substitute that in. And if we just look at that, we can see here BDPE equals CDE plus BDE, and that's completely identical to this one over here. Since these two are equal, we can conclude that BDPE is equal to triangle BDC. Now since BDC, remember, BDC is equal to 1/2 triangle ABC, we can substitute 1/2 triangle ABC here for BDPE. Therefore, BDPE must equal 1/2 triangle ABC. And yeah, this is in fact the configuration that you want. BDPE here satisfies what Bill wants. It's 1/2 the area of this big pasture and it contains P. What's good for us is since BDPE is 1/2 this triangle, it means the remaining area should also be 1/2. Notice the remaining area also includes P. P is being shared by both sides. So the remaining shape, I guess, is called ACEPD, so it's really long, but it's just this one here. So the way to prove that this is 1/2, also 1/2 the area, is we just say that ACEPD plus BDPE equals triangle ABC. Now we can just subtract BDPE from both sides. Then substitute BDPE for 1/2 ABC. And after we do that, it should be very clear what ACEPD's area is. ACEPD is equal to triangle ABC minus 1/2 ABC. And that is clearly just 1/2 triangle ABC. Since ACEPD is equal to 1/2 ABC and BDPE is also equal to 1/2 ABC, therefore BDPE must be equal to ACEPD. And that is how we solve this problem. We've satisfied both of what Bill wanted. Bill wanted two shapes which are equal and both shared the well, which is point P here. So yeah, that's just how you solve the problem. I hope you enjoyed my rambling. I hope you learned something, even just a little bit. And if somehow you didn't learn anything, I hope at least you found it entertaining, I guess. I hope you see it as a spectacle. And yeah, thank you so much for watching. Oh, and one last thing, this video took a lot of effort. Weeks of planning and then months of recording and editing. So I really hope you find this video at least nice. Yeah. I had to learn Python and stuff. Just oh my gosh. Alright, we're done here.